Okay, so we're going to have lecture today really relating to calculations of getting delta H, so that change in enthalpy. But this lab, I mean, I'm going to be straight up honest with you. This lab is a really hard lab to teach face-to-face because it is probably the most cumulative lab we have in the curriculum. And what I mean by that is the lab really touches on every component of this unit of thermochemistry. So pretty much all the types of calculations that we talk about in this unit are performed in relationship to this lab. And so students find this lab, even when we're together, a challenging lab because it brings so many topics together. So I didn't want it to live entirely asynchronously. We're going to do some of it together today as an application of the calculations that we're talking about today. So as we work through the session today, you might find it useful. I don't know why I titled this engagement. We're going to go into some breakout rooms, and I'm going to encourage you to share screens and annotate your lecture notes together to talk about how to solve some of these things. And we're also going to be using some tables of data in some of the calculations. And so I've linked you to the tables that are in your textbook. So if you click on that link, you should be able to get to the thermochemical data tables through the Pearson website, but you're going to have to log in with your Pearson ID to view that. I didn't have another way to link you to those tables other than that resource. You should also be able to click through to mastering and go to the e-text and find Appendix 2B. That's where the tables are. If you have an actual physical copy of the textbook, Appendix 2B is in the back of the textbook. And it's literally like 6 pages of data that you're going to be going through to solve these calculations. So we're going to be doing some of those calculations. So I'm trying to link you to that resource, or if you have the physical textbook, that could also be utilized.
Professor, can I ask a question real quick?
Please.
So will we be going over the week 11 lecture notes like during the Zoom today?
Today, we're going to be doing a lot of the week 11 lecture notes. That's right. There's a small portion, like 2.5 pages, that I've already recorded online. And I already know there's more here than we'll likely be able to cover today. So I have built in more practice calculations. So it's very likely I make a video of myself after today doing any problems we don't cover in the session today.
Okay, cool. Because then I need to go print it out right now.
Oh, okay. Yeah, it's going to be generally true that for these sessions, we're going to work with our week 11 or whatever week we're in lecture notes for the rest of the semester, and not those Google slides, because I just don't have time to build them. And I mainly have time to get us through the notes that we need to get through.
Professor?
Yeah.
This is more of a message to the class. I'm not sure how our Pearson account works, but in case someone doesn't have access to either the e-textbook or the textbook, please contact me and I can give you a copy of my ebook.
I don't know how the sharing permissions work on that either, but maybe you have the ebook in another way.
Oh, I scanned it from the library.
Well, there you go. That's another way. So put that in I'm gonna let y'all put that in the chat. Let's see. Where was I? I was looking for the chat because I don't know where it lives. Nothing's in the chat right now. Gerardo, can I nominate you to monitor the chat for me? Because you seem pretty good about that in the past.
Yeah, sure thing. Go ahead. I'll interrupt you if someone has a question.
Okay, I feel good about that. Okay, so where was I? Modules. Okay, so we're going to be working with that finding enthalpy page today and doing lecture notes. I put a couple of things in the module since Monday. I think it, I don't know how can I say this clearly? I've tried a lot of ways to get you all to talk about chemistry, and a lot of those ways have failed. So I'm going to just keep trying ways and let's see how this works. So a lot of you have said, I tried to go to tutoring and they weren't open in the hours that I went, or I tried to meet up with friends and I couldn't convene. So I kind of like this flip grid approach. I'm going to try it again. I built an assignment where I know you all are going to have some type of question about thermochemistry. A lot of this stuff is new. A lot of this stuff is unfamiliar. I want you to ask your questions. And I want you to help each other. Like, I want you to talk to each other about chemistry. And since we're largely asynchronous, how can we do this? Except I'm going to have you record yourself with one question you have about thermochemistry. You can totally put more in here if you want, but at least one question. Okay. And I set the flip grid so that you can't make an 18-minute video. You can only make a 1-minute video. So figure out what that question is and film yourself with that question. Put the link to your question in the thread. This particular discussion thread, you should be able to see anything anybody's posted at any time. I didn't make it not viewable until you've posted something. So you should be able to click here and see what other people are asking. So half of the assignment is just to ask a question. 2 points of the 4 points is just to ask a single question about thermochemistry. The other 2 points are that I want you to answer each other. So pick on one person's lingering question and answer it. Ideally, I want you to cite a section in your textbook or a page in your weekly lecture notes. So week 10 and week 11 are the weeks that we're doing thermochemistry. So telling how you would answer that and then answering it. Now, you don't have to answer in a video. It would be nice if you answered in a video so that it's like you're having an asynchronous conversation, but I'm not going to make you record 2 videos if that makes you really uncomfortable. Part of this class is explaining things orally, and part of this class is explaining things in a written response. So if you would like to answer their question in a written response, you are welcome to do so. I would ask that you only answer someone who doesn't really have an answer, unless you think the person who answered the other person is wrong. And then you can add your opinion and say, I kind of think we should answer it this way, and support your opinion in that. Obviously, I'll be monitoring this and get you the best information I can, but this is how I'm going to try to have us. I want to know what you're still confused about, because I really don't know at this point. Very few of you are coming to my office hours to tell me that you're having questions, which is somewhat frustrating. I really don't know what you're struggling with. And so I will definitely be monitoring this to see what your lingering questions are, and try to provide resources to answer those questions if I feel like your peers aren't answering you in a timely fashion. So I would recommend you stay engaged with this discussion thread, put your own questions there. I bet that you don't understand everything from last week. So if you have something that you still don't understand from last week, go ahead and make your video and ask away, okay? But then also monitor the chat, or monitor the discussion rather, and answer each other. So half of the assignment is being brave enough to admit what you still don't quite understand, and the other half of the assignment is figuring that stuff out. Okay. The other thing that I put in here is that I put several things in here. Can I be honest with you all? I'm feeling, as your instructor, really hard about this semester. And I want to stop sharing this one, and I want to share something else that I made this morning. So this is, you don't know who any of this relates to, but this is so far what's happened in our class. The blue slice of pie are people who have an A in this class right now, by the metrics I put in my rubric. The orange slice of pie are the B. The gray slice of pie is the C. D and F are people who are still enrolled, but they don't quite have enough points in the course yet to get to that passing grade. And then the green are the number of people who have already withdrawn. I've never had this before. This is insane to me. And I have to do better as your instructor. I can't continue to let people just not reach the success that they need in this class. I know you're all taking this class for a reason. I've had one person in my history of teaching General Chemistry 1 that took it to satisfy their GE with a lab requirement. Every other person who's ever taken this course with me is taking it because they need it towards their degree. And it is my goal as your instructor to help you reach the success that you want to have in this class. Am I the easiest instructor you're ever going to take this class with? Heck no. but I also know where you're going. And I know that 121 is no cakewalk. And so I have to know that when you leave 120 with a C or better, you have enough foundation to be competitive in 121. Because if you complete this class with a C, you can't retake it even if you wanted to. Okay? And if that foundation isn't strong enough, you're going to have a real hard time in 121. So I know that I'm a little bit harder on you than maybe some of the other instructors are being on students. I know I expect a lot of you, but you need the amount of practice that I'm assigning in order to get the repetition and the conceptual knowledge that you need to be successful in the next places that you go. And so I just have to take a deep breath, and I have to recognize that this semester totally sucks from all of our perspectives, from mine, from yours. This is super hard. We're all, as a campus, trying to figure this out in a way that is, I think, acutely painful to many of us in different ways. I don't want you to languish alone. I want to be your partner in this, and I want to support you, but I cannot do so if I never see you. I cannot do so if I never hear from you. So if there is a way that I can support you, I want you to let me know that. Having said that, I can't have my graph look like that next semester. I have to do better. And so I want to know from you as a student and the student experience in this class, what can I change to help more students succeed next semester? Because I'm teaching this again. I want this to be, I want to change variables that help people to be more successful than they've been this semester. So I want to know what your experience is like, and I want to get better. And I am asking you for your name on this evaluation survey, but I'm not going to have, I don't have any time to do anything right now. So I will not track your responses with your name. I'm only asking your name so that you get those 5 points. Okay. So please take a minute to fill out that form. Let me know what your experience has been like, and let me know what I can do to make this a better experience. I'm almost crying right now because I'm really emotional, because I mean, I put all of myself into teaching, and this has been a really humbling semester for me, if I'm being honest. And it is my mission to help every single one of you get the support that you need to reach your goals. So let me know if there's a way that I can be of assistance. We're running short on weeks to do it. We got 5 more weeks to go. So let me know as quickly as you can, because we've only got so much time left together. Okay. I just put this back in here. This is not new. This is something I put a couple of modules ago, but you have December 4th to do it. These are 3 options of videos to watch. If you are completely burned out and you need to think about something else, this might be a nice assignment to check off your checklist, is just go watch a movie this weekend and complete that assignment. And one other thing I added two other things I added. So last week we watched ice melt, and I wanted you to tell me your explanations for why ice melted. If you did not join us for last week's lecture, I've linked you to all the resources to make the observations. I want you to finish your entry in the collaborative document. So I want you to try to use the vocabulary that we introduced last week: heat, heat transfer, thermal energy, temperature, to explain why ice melted faster in one solution than the other solution. So again, this is a Google Doc. There's a table, initials for every person in the class. And so find your initials and type your responses here. If you did not get a chance to come last week to lecture, it's okay. I put the videos here that we use to make those observations. So I want you to asynchronously watch ice melt and think about why ice is melting differently. You are welcome to talk to each other about this in an effort to get what you think is the real explanation for why one melted faster than the other.
I have a question.
Please.
So, well, it's kind of 2. So is this pretty much for whoever missed the last lecture, or is it also for us who did come to the last lecture, but you want us to do the last point where it says to comment on a another classmate who I made a prediction. So do you still want like all of us to do this assignment, or is it just for the people who I missed last week's lecture?
It's both of those things. So if you did not come to lecture last week, I want you to make those observations and predictions. I want you to watch the videos and see if your predictions match the observations. And then I want you to do that last explanation. For those of you who came to lecture last week, I want, if you didn't have a chance to go back into the document and make your last explanation, please do so. And then as Tajay mentioned, there is one part of this that's using the comment feature to comment on a classmate who doesn't have comments and explain any ways that your explanation might differ from their own. Remember, use language like I think that, because, and cite things that you think, like places in your textbook that gave you that inspiration, web resources that gave you some inspiration. You may use whatever resource you want, but thank you for reminding me that I did add a comment feature. So since all of you are editors of this document, you should also be able to, let's see if I can link to the document. You should also be able to use the comment feature, which is this little box right here. It looks like a little word bubble with a plus. So I can highlight, maybe I want to talk to this friend, and I can add a comment, and it'll go over to the right-hand side and you can put your comment here. Okay. Everybody clear on that one? Last thing. I put in another extra credit option. You just should have received an email that I have finished grading your most recent exam, both versions, the one you took in prime time and the one you took as a take home. It wasn't 100% for the take home. There are still things to learn from the take home. And I did not have you really do a reflection on assessment 1. Our final exam is 5 weeks away from today. There isn't a whole lot of time left for us to master these skills in the course. So I'm building an extra credit assignment where I want you to take your PDF of your submission. For assessment 1, it's whatever PDF you uploaded to Gradescope. If you already deleted that file, I do believe there's a way you can download your PDF from Gradescope. If you need support with that, let me know. For assessment 2, I recommend you use your better version, which I think for everybody was the take-home assessment, unless you opted not to take the take-home assessment. And I want you to go through that assignment, use the keys, and I have linked you to all the keys to all the versions here. So you should be able to see my handwritten work for each problem. And I want you to go through that file and correct your work. So I made comments in Gradescope. Maybe they make sense, maybe they don't. I want you to use the keys, use my comments in Gradescope to help you make corrections. Please use a different color of ink than you use to take the assignment. So I actually want to see what corrections you're making to your work. I also want you to write notes to yourself, like, why did you lose these points? This was a silly sig fig error, or I did not know this vocabulary. And help yourself. Cite some pages or section numbers. I will inspire your final exam as a mastery assessment, which means I've tested you on several assessments through the course. I'm going to take what you didn't necessarily have on each of the individual assessments, and I'm going to try to bring that out and see if you got it by the end of the semester. But really, it is a more holistic look. I cannot be as granular on the final exam as I am on each individual assessment. So I'm really looking at big picture items, things that you have, skills that you simply have to be successful in the next step in our sequence, which is 121. That's really my focus. And we can talk about final exam assessment more in a little bit. Right now, my main focus is to say through this assignment, this is how I want you to figure out what is it you didn't know day of, and what is it you didn't even realize or have full mastery of for the take home, and learn it by the time that it's that final exam. So you're going to get 4 points for each assessment that you do this for. So up to 12 points. You should be able to upload multiple files to this assignment, so you can upload them as you go. Please don't put them all off until the last week of class. Please actually take your work and try to do this reflection now when you have, I know it doesn't feel like you have any time, but trust me, you have more time now than you will have later in the semester. Go back through and try to correct your work and think about what it was you didn't necessarily know. Get those skills, review anything you need, bring it to office hours if you need, go to tutoring if you need. Any of those options are available to you. 4 points for each assessment, so up to 12 points total. You have until midnight, basically, on the Tuesday before your final exam, which is a Wednesday. So I have to receive your corrections, your debriefing, as I'm calling it, by that night, December 8th, for you to receive the extra credit points. Anybody have any questions on that? Oh, the chat is lighting up.
Is there
All the questions have been answered in the chat. You're good.
Okay, cool. All right. I thought I heard somebody ask something. Are we all good? All right, we're all good, I hope. Okay, I'm gonna stop sharing that. So we are in our week 11 notes. Let me start sharing this. Come on, you can do it. Well, this is anticlimactic. Hang on. What Wi-Fi am I using? Why am I not connected to Wi-Fi? Okay, now maybe this will work. I'm not gonna cuss. Can take a deep breath.
Want to take a 5-minute technical break?
I might need it. Let's see if I can just log into Zoom. This is how I have been doing it. But I found another way. And
Well, if you'd like, while you're trying to fix that, I just want to remind our class that please don't drop the class if you are thinking about it next week. Please consult either the professor and even our assigned counselor, Alicia. I'm sure they'll give you a better scope of like what your outlook is on class. So please don't do anything before consulting them. That is all.
All of that is definitely true. All of that is true.
Please also consider using our Discord.
That is also true. What are we doing? We're Wednesday synchronous. Let's start.
Maybe we're all stuck in an Apple commercial.
Okay. I'm stopping sharing that. I thought I was sharing this. Now I am. Okay, we did this. We did it. Okay, I'm back on. We're talking about enthalpy. We're still talking about enthalpy, delta H. Today we're going to talk about a lot of ways to calculate delta H. I did do an, excuse me, I did do an asynchronous lecture, which walks you through how we can get delta H from bond energies. And so that's sort of a chapter 10 topic that I'm bringing back into chapter 7. So there is one way that you should know from your asynchronous lecture for calculating delta H. Today is about a lot more. So there's this old dead guy, Hess, who has a law that's pretty much, it's a lot more general than just bond energies, and it's actually more general than just the thermochemistry chapter. We've done this before. I've given you assignment problems where you have multiple reactions to get to a given product. Not everything in chemistry happens in a single step, as you see in your textbook. Almost nothing goes to completion, as you see in your textbook, so that's unusual. Hess literally states that given a set of reactants, and products, delta H is the same whether the process occurs in a single or in multiple steps. So it doesn't matter whether we do this chemical reaction in a single step or whether we take 8 steps to achieve it. The overall change in enthalpy for the process should be the same. That sort of also relates to the first law in thermodynamics. Energy only changes form. So whether you are doing something in a single step or multiple steps, that the delta H, the overall delta H for the reaction should be the same. There are 2 important things to keep in mind as we go through this. Number 1, if a reaction, say you're given multiple steps, and you'll know it's a Hess's law problem. If it gives you, anytime the problem gives you multiple reactions, this is literally screaming, Hess, here are some possible steps, and here is the net equation that you're trying to get to. So if you need to reverse one of these steps, that is, swap what's the reactant and what's the product to build that net reaction, if a step is run in reverse, what should happen to delta H? Is delta H the same? So for instance, let me give you a for instance. This is a possible step that I can use to achieve this reaction. This delta H is positive. What does that mean? What does a positive delta H mean?
It's exothermic.
Does energy go in to make this reaction occur, or does energy get released by this reaction?
It gets put in to break the bond.
That's right. I have to, and a positive sign in thermochemistry means I have to put energy in to that process. So a positive sign means I'm putting energy in to make that process occur. So am I endothermic or exothermic?
Endo.
I'm endothermic. That's right. So
Is that
what
the
if I
cold
were,
one or the hot one? That's cold, right?
so if I'm, you tell me, if I, as a system, as a reaction, if I need to take energy from the surroundings, is my flask going to feel cold or hot?
Cold. No.
Cold. Remember, the flask is a surrounding.
Yeah.
It's not the system. So the system is just that chemical reaction. So if the reaction is endothermic, it's going to take energy from anywhere in its surroundings, the solvent, the flask itself. And so overall, that flask should feel colder.
Like a cold.
Now, what happens if I run the reaction in a reverse? What happens if nitrogen monoxide becomes the reactant and nitrogen gas and oxygen gas are the products? Is that endothermic still, or is it exothermic? What do you think? Maybe let me just put that hypothetical. If I run this reaction, how does delta H1 relate to delta H question mark?
Equal but opposite sign.
I agree, Chris. I agree. If a step is run in reverse, then delta H needs to have the opposite sign. You need to swap the sign. So if I run this reaction in reverse, then this step would have a delta H of negative 180 kilojoules. I would release that amount of energy. That would be an exothermic process. Theoretically, any chemical reaction that you see written could be run in reverse. Practically speaking, the energy barriers can be too high. I'm going to let that be a topic for 121. But just so you know, as we're doing Hess, if you need to swap the order of a step, you can do so. But for delta H, you need to also swap the sign. Second thing to consider. As we talked about last week, delta H is proportional to the mole coefficients in a reaction. What do I mean by that? This is that $25,000 word I used last week, thermochemical equivalence. This 180 kilojoules has to be absorbed if 1 mole of nitrogen gas is to be used in this process. This amount of energy has to be absorbed if 1 mole of oxygen gas is to be consumed in this process. This amount of energy must be absorbed to produce 2 moles of nitrogen monoxide. So all of these molar coefficients are related to that amount of energy. So let's make a change. What if I change the coefficients to those? What is the relationship of delta H1 to delta H question mark?
Would it be halved?
It would be halved and negative. So I'm taking those molar coefficients down by half, but also this reaction is the reverse of this reaction. So I'm sorry for doing 2 things in one step. Sorry, not sorry. Delta H is proportional to the mole coefficients in the reaction. So if you change the coefficients, in doing Hess, then you must also scale delta H by the same amount. So in this process that I just did as an example, we have those molar coefficients, then we also need to have delta H. Okay, so cut that in half. These rules will make more sense as we apply them. Okay, so let's just go through the problem solving process as you would do it for Hess. So this first example I've basically done for you. If I were to add these 2 steps together, overall, I would get this net reaction. So these are my steps that are allowed by Hess, and that's my net reaction. How is that my net reaction? Well, I see nitrogen monoxide as a product over here, but it's a reactant over here. So when I add these 2 together, 2 NOs going to 2 NOs, well, nothing overall chemically changed. So that species disappears. And so when I add these up, what remains are the things that are in boxes. Okay, everything in a box didn't get eliminated. So it is still there. Everybody with me so far? I got N2 as a reactant. I've got 2 oxygens as a reactant, and I've got 2 nitrogen dioxides as a product. That's what I overall would get from summing these. If you add steps, then you also can add delta H's, and that is Hess's law. So delta H3 is literally delta H1 plus delta H2. I add those two changes in enthalpy of the individual steps, and I get the change in enthalpy of the overall reaction for my net reaction. How are we holding up? If you don't know this by now, I'm going to ask you to draw some things in this class. And so for this unit, I've been drawing energy diagrams. Now that we're really into H, you're going to see me calling them enthalpy diagrams, which just means that the energy that I'm looking at is enthalpy, which, as we learned last week, is basically the heat contribution from the process. So we're ignoring work. We're not thinking about the amount of work that these chemical reactions are doing. We're just focused on heat transfer from the chemical reactions. How are we doing so far? In building enthalpy diagrams, you got to start somewhere, right? So I'm going to start with my reactants of my net reaction. So I've got nitrogen and I've got 2 oxygen molecules. So here's the energy level for my reactants in my net overall reaction. Now, what happens if I do reaction 1 to these reactants? If I do reaction 1 to these reactants, I've got to add in 180 kilojoules of energy. If I put 180 kilojoules of energy into this system, then what overall has changed? I have taken that nitrogen molecule and 1 of those oxygen molecules, and I have formed 2 new NO gas molecules. But 1 of those oxygen molecules didn't react. So I still have that compound. Everybody with me so far? Now, what happens when these things react? The 2 nitrogen monoxides with the oxygen. I form a new product. I form 2 new NO2 molecules. In doing so, that is an exothermic process. I am releasing energy from that process to the tune. Oh, why did I go lower? I should stay on my lecture notes. So I went up by 180. I'm only going to go down by 112. Relative energy matters in this process, folks. So I realized that I looked up there at the net and I was positive and I was about to get a negative delta H. I go down less than I went up. So overall in my diagram here is delta H3, or in other words, I'll put it here, delta H3. So if I put a dotted line, if I want to think about this in terms of the amount of energy overall for this net process, that is a positive value of 68 kilojoules. So when I add those 2 steps together, overall, I have to put in energy to make that process occur. Since I think these concepts are a little bit hard, I thought what I'd do is start to use colors to help you sort things out. And also remember, what does NO and exothermic mean? So this is an endothermic process. I get colder. I have to put energy in to make that occur. I have to go way uphill. When I form these new bonds, some energy is released. This is an exothermic process. Energy gets released. But overall, I had to put in more than I got out from building these new bonds. And so overall, my net process is a positive enthalpy. I have to put energy in to make that net reaction occur. Remember, positive delta H means endothermic, putting energy in. How are we doing? I've talked a lot. So if I ask you to build an enthalpy diagram for a Hess's law problem, this is what I'm asking you to do. I want you to set levels for reactants, products, and you can have separate levels for any intermediate steps. On those levels, you put compound formulas. The number of atoms and the type of those atoms should be the same on every level. Otherwise, you don't have a balanced process. What do I mean by that? On this level, I have 2 nitrogen atoms and 4 oxygen atoms. On this level, I have 2 nitrogen atoms and 2 plus 2 is 4 oxygen atoms. On this level, I have 2 nitrogen atoms and 2 times 2 is 4 oxygen atoms. So every level should have the same number of atoms of each type. Use up arrows for endothermic. Use down arrows for exothermic. And I'm not going to rigorously, like, these are drawings after all. So I'm not going to be super strict on this goes up 180, but this only goes down 112. Is this enough space right here? I'm not really going to be strict on that. Overall, if this is an endothermic process, then you need to have set your relative levels so that your products are higher in energy than your reactants. The length of this line versus this line versus this line, I'm not going to be super strict on that. Does everybody understand what I mean by that? So set your levels roughly 180 up and 112 down, but there's no way I'm going to get out a ruler. Ultimately, what I want is if your overall process is endothermic, then your overall arrow to get to that from your reactants to your products should be uphill. If it's exothermic, then the overall arrow to get from the reactants to the product should be down. Cool?
I have a question about the energies for the delta H's. If we're given those energies in kilojoules, we'll always use that as opposed to using the table that was given in that asynchronous lecture.
So the asynchronous lecture gives you bond energies in kilojoules per mole. Typically, when we're talking about chemical reactions, we're talking about a lot of energy because a mole is a lot of atoms. Okay? So, whereas last week, when we were just looking at heating and cooling objects, that was more on the scale of joules. It doesn't take a lot of heat energy to heat or cool a thing. But reactions themselves can produce or can absorb lots of energy per mole of a substance. You're rarely dealing with moles of the substance on the other hand. So all I'll say, Alex, is that you want to make sure, and we're going to have some examples today where the units get a little confusing, use the same magnitude of energy. So if everything in your diagram is kilojoules, it all needs to be kilojoules. If some things are joules and some things are kilojoules, well, then that's incorrect. You want them to be all in the same unit of energy. Typically, when I'm asking you to do enthalpy diagrams, that is the unit of kilojoule. But when we do some calorimetry calculations in a little bit, we're going to have kilojoules and joules. And so you got to pay attention.
Okay, thank you.
All right, let's think about this a different way. What if this was our net reaction? What if this is the delta H that we wanted to know? And these are the possible steps that we could use to get that net overall delta H. I want to show you how to use Hess's law as a process. So my first problem solving strategy is to pick a species in the net reaction, sorry. That is only found in one possible step. Pick a species in your net reaction that's only found in one possible step. Okay, well, here's nitrogen as a reactant, and here's nitrogen as a reactant. It's only in that step. Does everybody see that? Once you found a step that has a single reacting species that's possible, flip any reaction, any step that needs to be flipped. Scale any coefficients. That need to be scaled. So if the step has a delta H, when I flip the step, what happens to delta H? What do I do to delta H?
Change the sign.
I change the sign. So if I flip that step, then I have a negative delta H.
And are you flipping it to get the reactant to the product side, or the product, they're all on the reactant side, or are you going into that?
That's a great question, Emily. So my first step that I picked, N2 plus O2 yields 2 NO2, I don't have to do anything to that step because N2 looks the very same as it does in my net reaction. You with me so far?
Yeah.
But now I need to get rid of that NO2. Well, in this reaction, it's a product, as it was in this reaction. If I want to get rid of the NO2, then I have to flip this process. I have to turn it around, okay? So I'm going to say 2 NO2s yield 2 NOs plus O2. Yeah?
Well, I think, yeah.
But I feel like now I've confused myself. Did I
Well,
translate?
the original problem is 2 NO, and then you wrote 2 NO2s, but that's the final product. So I don't know if that's what you were getting into.
Hang on, I'm getting backwards. This is going to go away. What did I transfer wrong? Did I do a copy and paste error?
Yeah, I think the first one, it's 2 NO, not 2 NO2. The first product. Sorry, to make it clearer. Unless you were going all the way across.
Usually you wrote the delta H3 as the net.
Well, I know, but all I'm doing here is swapping the steps. I don't think I'm having a senior moment. Hang on.
Because I think in the first step, you have 4 oxygens on one side and 2 oxygens on the other side. It's not balanced.
Oh, I know what I did. I didn't put the 2 there. That's important. Okay, watch. So there should be, and I still didn't put it there. Okay, so this O2 is going to go away and I'm going to be left with only one O2. That's what. Okay, so I have my N2 and I have my O2 and it's yielding 2NO, which is the reaction whose delta H I want to know. Does everybody see that? It's very important when you're taking your steps and you're manipulating them that you carry the same coefficients, because that's pretty critically important. Now, this first step is delta H3. I did nothing to that reaction. I didn't flip it. I didn't scale it. What did I do to delta H2? In this process, I took this second step and I swapped it. I made the products be reactants. So in doing that, I need to have the opposite sign of delta H2. In other words, I'm going to take 68 and I'm going to subtract negative 112, which is the same thing as adding 112. And what do I get? 180 kilojoules. That would be my delta H1. What is that? I want you to build an enthalpy diagram, or help me build an enthalpy diagram. So let's just start with our products, or sorry, with our reactants, N2 and O2. I still need 2 O2s, right? I still need 2 O2s because I have in order to do the steps that I'm going to do, I still need 2 molecules of oxygen. Okay, so my first step is delta H3. What does this chemical reaction do to this process? I'm going to go up 68 kilojoules. What do I do in this chemical reaction to N2 and 2 O2s? I form what?
2NO.
I form 2 NOs. Not 2 NOs, 2 NO2. Yeah? So in the next step, again, I had to add energy because I'm swapping this step. So I'm taking those 2 NO2s and what am I forming? I'm forming this line should be a little longer than that line. I'm forming 2 NOs plus O2. So that's delta H2, which is now positive 112. That's my step 2, where I still have to add in even more energy. Now, overall, in this process from delta H, so here, this is my delta H1, I have to go up a huge amount of energy, 180 kilojoules. And one of those oxygens is not needed overall or doesn't chemically change overall. But as I said, every level needs to have the same number of atoms on it for these diagrams to be accurate. So in both of these cases now, I had to add energy. Both of these steps are endothermic. So overall, this process would be hugely endothermic. How are we doing? So in this application of Hess, we flipped a step. Whenever you flip a step, you do the negative of the delta H for the original step. In this case, we didn't scale anything, but if you need to scale any coefficients and the step had a delta H, let's say you scale the step by 2, then your delta H is twice the delta H. I feel like we need more practice. Do you?
Yeah.
Sorry, Professor, can you just go back? Can you explain to me why is it that you got rid of the coefficient of 2 only on that delta 3?
Sure. Because in this reaction, I don't have a coefficient, but it's implied to be 1. And in this reaction, I have a coefficient of 2. So there are 2 oxygen reactants, but only 1 oxygen product. So I only get to cancel one of them. So there's 2 moles on the reactant side, but there's only 1 mole on the product side. So they don't both get to go away. Only 1 mole goes away because only 1 mole overall doesn't change. Do you see that? So even at the end, on my very last step, I have an intact molecule of oxygen. Chemically, that molecule doesn't change.
Okay, looking at the net.
Yep.
Okay.
So in the net reaction, only 1 mole of that is changing.
Okay.
But for every level to have the same number of oxygen atoms, I need 2 moles of oxygen available.
Okay.
How are we doing? I'm going to give you all.
Could you scroll back up really quick? Stop. I just need the text.
So there's a practice problem on the next page. I want to give you, let's say, at least 5 minutes, and I'll check in with you if you need more time. 5 minutes to approach this problem. How would you use, and this time I gave you 3 steps. How would you use your 3 steps to get to the net reaction? Remember these steps. Pick a species in the net reaction that's only found in 1 step and build from there. Should we do this one together and I let another example be on your own?
Yes, please.
Possibly. This one looks crazy.
Don't worry, the next one has 4 steps. So if we do this one together, you got 4 steps on your. Let's do this one. Okay, here's my net reaction. First order of business, find a species in that reaction that's only present in 1 possible step.
Delta, the H1.
I'm talking about reactants or products. Find a chemical compound that's only present in 1 possible step. So again, this is my net, and these are my possible steps. What's something in this reaction that's only found in 1 step? Call it out when you have it. Unmute yourself.
Multiple people in the chat have said F2.
Okay, F2. Which step is it in?
The 3rd one.
3rd step. Okay, great. Let's start with step 3. That's fine. It does not mean, just because I list the steps in an order doesn't mean you have to think about them in the order. And as you start tackling book problems, it doesn't mean every step is used. So that's even crazier. Okay. So I'm going to take this reaction, F2 plus O2 yields 2F2O. Do I need all of those coefficients as written? Do I need this step to be in this order? Here's my net. How many F2s are in my net reaction?
Just one.
Just one. How many are in my step?
8. No, wait. I'm sorry. I'm looking at the net. My bad. 4.
2. There's 2 in my step.
Oh, I'm looking at the wrong step. My
There's
bad.
only 1 in the net. This is a reactant. Is this a reactant? Yes. You do know your. So I don't need to flip this. Do I need to scale it? Yes. I need to scale it. I only need half this amount of F2. So what do I have to do to delta H3?
Divide by 2.
I need to divide delta H3 by 2.
Oh, and I guess that answers my question too. So you want reactants from the steps to match up with reactants from the net. You want them all to, like if it's a reactant on one side, you want it to be reactant on the other, or the opposite. That was kind of my question from earlier that I'm confused on.
Yeah, well, so let's take CF3, ClF3. Let's take chlorine trifluoride.
Okay.
It is a product here. Everybody see that? It is a reactant here. So what do I need to do to step 2? To build the net reaction. I don't want ClF3 to be a reactant. I want it to be a product. So I need to flip step 2. Everybody see that? I want ClF3 as my product. But in my step, it was a reactant. So I have to flip it. Am I done manipulating this reaction? Do I need 2 ClF3s?
No.
No.
No, I only have 1 mole of ClF3 in my product side. Does everybody see that? And I have 2 moles of ClF3 in this step. So what else do I need to do to this step?
You get rid of the 2.
I got to multiply everything by a half.
Oh my goodness.
So what happens to delta H2? What do I need to do to delta H2 to deal with all the things I just did to this reaction?
Negative sign and divide by 2.
I flipped it and I scaled it. So I got to do both of those things to delta H2. Since I feel like it can be hard to track this stuff, keeping the original coefficients, I'm going to go ahead and divide by 2 for everything. So that becomes 0. That becomes 1. This becomes a half. And that becomes 1. This is a half. This is 3 halves. This becomes 1. This becomes 1. How are we doing? Have I given everybody enough time to think about this one? So
I'm sorry, can you just, so that ClF3 was a half before we made it into a 1?
that ClF3 was a 2.
Oh, that was a 2 before.
We
Okay.
divided the 2 by 2 and we got 1. So far, so good. So I want you to do step 1. How do I add step 1 to these 2 steps that I have in a way that gets me my net reaction? Don't answer out loud. I want you to do it on your own paper, and then I'm going to ask for a volunteer. So take a minute. What would you do with step 1? So I need chlorine monofluoride. It is found in step 1. Is it a reactant or a product here?
It's a reactant.
Is it a reactant or a product here?
Reactant.
Also a reactant. So do I need to flip this?
Nope.
How many moles of it do I need?
Just 1,
How many moles are in this one?
2.
So what do I got to do? Is it Jason?
Huh?
Who's speaking with me?
Oh, Evan.
Okay, so what do I got to do, Evan?
I just scale it.
I
Multiply
got to
by
scale it by what?
1/2. 1/2.
Yeah, okay. So I'm going to scale it by half. So CLF plus half an oxygen yields half Cl2O plus half F2O. So if I halved it, I've also got to take delta H1 and divide it by 2. Everybody with me so far? So in order to know that I've done everything right, everything that's not in a box should cancel. Let's go one by one. I have one F2O over here. I have another half of an F2O down here. 1/2 plus 2/2 equals 3/2. Bye, Felicia. All right. I have 1/2 Cl2O over here. I have 1/2 Cl2O over here, so those go away. I have half an oxygen and half an oxygen. So 1/2 plus 1/2 is 1 mole. I have 1 mole over here, so those go away. That's another way to check your work, is to make sure that everything that's not in your net reaction cancels. Now, I want you to mathematically solve for delta H4. I'll give you 2 minutes. Solve for delta H4. What do we get? Is it in the chat? Nope.
One unit says it's negative 108.7 kilojoules.
I failed to write it in my notes. So did everybody get that number? I have the math written. I just didn't write the mathematical answer, and I definitely don't have my calculator. It seems like it's supposed to be exothermic, so I feel good about that. Does everybody agree? Negative 108.7 kilojoules?
Yeah, I got that too.
Great. I'll update my notes. How we doing, folks? So that's Hess. Okay, we're going to come back to Hess in a little bit when we get to the lab portion. So I want you to hold on to that thought because I got other things to tell you about. Actually, I mean, this next topic is also an application of Hess. Hess is never going to leave you now that you know about it. You'll see it everywhere. How are we doing? So here's where you just want to throw your book on the ground, okay? All this time, I've been writing delta H's with no degree symbol, and now all of a sudden a degree symbol pops up. And you're like, what am I supposed to do with this? Okay? That little degree symbol means standard enthalpy. Standard enthalpy. Anytime you see a degree symbol, it means that that enthalpy was measured at standard conditions, which, as if chemistry wasn't confusing enough, is different when you talk about gases than when you talk about thermochemistry. So in gas land, standard temperature and pressure was what?
1 atmosphere, 273.15
Kelvin. Okay.
Kelvin.
Which is how many degrees Celsius?
0.
0. Okay. So in gas land, standard temperature was 0 degrees. In thermochemistry land, it's room temperature. So that's different. So that degree symbol for standard conditions in thermochemistry means you're at room temperature. And one more thing, it means your concentration for your reactants is 1 molar. So if you have aqueous reactants, the concentration of those reactants is 1 molar concentration. Those are standard conditions. So when you see that little degree symbol, it means standard enthalpy of formation. The literal definition of standard enthalpy of formation, it gets a symbol delta HF with a naught, F standing for formation, is the amount of heat required to form 1 mole of a substance from elements in their standard state at 1 atmosphere and 298 Kelvin. So if I'm a compound and I'm a gas, then my pressure is 1 atmosphere and my temperature is 298 Kelvin. If I'm a solid or a liquid, then I am a pure solid or a pure liquid. At 298 Kelvin. If I am aqueous, that means my concentration is 1 molar and my solution is at 298 Kelvin. As you're working through problems, it's important to remind yourself what standard conditions mean. For any elemental substance, the heat of formation is 0. If that is the state of that substance under standard conditions. So what is the state of matter for hydrogen gas? Oh man, I said it, under standard conditions. I can't stop myself. Gas, okay? So the heat of formation for hydrogen gas is 0. It doesn't take any heat to form that elemental substance. Oxygen, what form?
Gas.
Deep breath, gas. Gaseous, you are in a room that is at roughly 298 and a pressure of 1 atmosphere. You are breathing oxygen gas. So oxygen is a gas under standard conditions. Things like there's only 2 elemental substances that are liquid under standard conditions, bromine and mercury. And there are lots of solids. So like sodium metal or iodine is a solid, which is unusual. The halogens are where it gets really interesting. So F2 and Cl2 are gases. Bromine is a liquid and iodine is a solid. So these are the substances in their standard states at standard conditions. So the tables and tables and tables in the back of your book of data look something like this. Actually, the tables in the back of the book have a whole lot more thermochemical data. This table that's embedded in the text is just delta HF. But what you'll notice is here's bromine as a liquid. It has 0 delta H. Here's chlorine as a gas, 0 delta HF. Fluorine as a gas. Wait, what are they doing here? Oh yeah, okay, sorry, my pointer. Fluorine in its natural state, F2, that's the elemental substance, is 0. If I want to break it into individual fluorine atoms in the gas state, that requires energy. Naturally, fluorine comes to us as F2. If I want to break it up into individual fluorine atoms, I have to break a sigma bond. That requires energy. So just orienting you to the way that you're going to see data in these tables. Oxygen in its elemental form most abundantly is O2, but we also have ozone. It takes a little bit of energy to make ozone. So the state of matter matters. Here, sodium metal is 0. If I want gaseous sodium atoms, that takes some energy. So when you're pulling data from these tables, I want you to be very aware. Sometimes you're going to get 0. When you get a 0, it's likely an elemental form of that substance. If you're trying to pull delta HFs, make sure you're pulling the correct state of matter, because that also matters. For instance, here I'll just go ahead and point out water, gaseous versus water liquid, they have different heats of formation. So when you're trying to calculate things with heats of formation, pay attention to states of matter.
Professor?
Yeah.
I just had a question because I was trying to notice trends in that table. Do all diatomic molecules have a 0?
If you come to us in nature as a diatomic elemental substance, then yes.
Okay.
So there, I made you memorize a couple of diatomic elemental substances: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine.
Have no fear and ice cold beer.
Those are all diatomic elemental substances. Okay. It looks like in the 5th edition of your book, they have corrected this confusing thing about solutions, but I don't know if they've done that for all problems or just the ones that are in your lab. So I want to make sure I call out a note about strong electrolytes. So if you have hydrochloric acid aqueous in your reaction, that is a strong acid. In solution, it dissociates into H plus and Cl minus. That's what strong acid means. So I don't have any HCl in solution. I have H plus ions and I have Cl minus ions. Everybody with me so far? So in older editions of the textbook, so if you're using the 4th edition, if you go to the back of the book, you might not be able to find a delta HF for hydrochloric acid aqueous. What you should be able to find though, is a delta HF naught for H plus and a delta HF naught for Cl minus, both aqueous. So if you want to know the delta HF naught for HCl aqueous, you can add the delta HF naught for those ions. This one is 0. This one is negative 167 kilojoules. So overall, negative 167 kilojoules. So if there is a strong electrolyte in your reaction, then you might need to add the delta HFs of the ions in order to get the contribution for that chemical compound. Remember, delta HFs are for 1 mole. So that's the amount of heat per 1 mole of HCl. How are we doing? Now, I defined standard enthalpy of formation up here. The amount of heat required to form 1 mole of a substance from elements in their standard state at 1 atmosphere and 298 Kelvin. So here is literally a reaction that would give you a delta HF. Let's unpack this definition. This reaction forms 1 mole of the species H2O that's a liquid. Everybody see that? My product of this reaction is 1 mole, which is why you get some funky coefficients on the reactant side. The definition of standard enthalpy of formation is the amount of heat required to make 1 mole of that thing from elements in their standard states. Remember, this delta H is proportional to all the molar coefficients that are in that reaction. So when you see delta HFs and the reactions that go with them, you're going to get some half coefficients because of that definition. Elements in their standard state. So for this case, hydrogen gas and oxygen gas. Those are both elements in their standard state. Those are the reactants in this reaction, are elements in their standard state. The last thing I'll call your attention to is that states of matter matter. If I were to take hydrogen gas and oxygen gas and try to make H2O gas, the delta HF for H2O gas is not the same as the delta HF for liquid water. It is negative 241.8 kilojoules. So different. So when you're pulling these delta HFs from the back of the book, make sure you're pulling the correct state of matter. You can use delta HFs to calculate delta H for any reaction using this mathematical relationship, which I will give you in potentially useful information. you can add the sum. So this is my big epsilon sum of the moles of product times the delta HFs of products minus the sum of reactants times the delta HF of reactants. If you've already viewed my asynchronous lecture, you might realize this is a little bit swapped for the using the bond reactions, bond association energies. In that form, reactants were on this side and we subtracted products. Well, this is a different process. In this process, delta HFs are defined as producing the compound on the right. So products are on the right. So the delta HF signs should stay alone. But we need to reverse the signs of the delta HFs for reactants because the reactants are products in their heat of formation reaction and we need them to be reactants. So that's why we subtract that contribution. Let's calculate a delta H using delta HFs from the back of the book. I would love it if you could link to those tables, but I think all of the compounds that we need are in your lecture notes. So I want to treat this like a Hess's law problem. I know I want that as a product. So one of my steps needs to make some carbon dioxide gas as a product. Well, how would I make that? I would make it from carbon in the solid state and oxygen in the gas state. The delta HF naught for that reaction from my table, negative 393.5 kilojoules. Okay. Same thing for my next product. This time I want 2 moles of liquid water. I want 2 moles of liquid water. Well, that means I need 2 hydrogen gases and an oxygen gas. What do I need to do to that delta HF? I need to multiply it by 2 because the one that I find in the back of the book will just be for 1 mole of water. My product has 2 moles of water. So I have to multiply that heat of formation by 2. Everybody with me so far? Right now, I have my 2 products. Right here in this process, what I'm doing is adding up the sum of the moles of products times the delta HF of products, which is right here in my mathematical term. I'm adding up, here's my moles, 1 mole, 2 moles, here's my delta HFs. These are found from the back of the book. Well, now I have my reactant, methane. I need it to be a reactant, and I need 1 mole of it. Well, it came from carbon and hydrogen. If I look in my table, here's methane gas. I have a delta HF, but that's to form methane. Now I'm breaking up methane, so I need to change the sign of delta HF. I need negative delta HF. So instead of negative 74.6, I am going to add 74.6 kilojoules. All right, in adding this reaction, hydrogen gas goes away, carbon solid goes away. You will see that I have elemental oxygen and I have 2 moles of it from my steps. What's the heat of formation of oxygen? Gas.
0.
0.
0, because oxygen gas is an elemental substance. So I could add 0, but it's already there because it's defined as how these reactions come together. So if I wanted to do the contribution on the reactant side of oxygen, I would do 2 times 0, which is 0. Delta HF for oxygen is 0. I add those up and my heat of reaction is going to be a standard enthalpy, and it is going to be, if I sum those up, I get negative 890.5 kilojoules. How are we doing? Down here in my reaction, this is negative the sum of the reactants times the delta HF of the reactants. So here I'm subtracting the delta HS from my reactants. I'm never going to ask you to write this out like Hess, but I just want to show you the origin of this relationship. It will always be there for you, but I need you to know what it means and why it works. It's just another application of Hess. So if you are asked to calculate delta H naught, then you can do so with delta HS from the back of the book. That little degree symbol should be a hint to you. I can use those appendices in the back of the book. How are we doing?
For exams, those numbers will always be provided, correct?
I will give you tables and tables and tables of data. I will give you tables and tables and tables of data. How are we holding up?
Wait, I tried to do the numbers and I didn't get the same numbers. Could you just, so you did the negative 393. Is it plus the 2 times negative 285?
Did I not plug things into my calculator correctly?
No, I don't know. I think I'm plugging it in wrong. So I'm just want to.
So negative 393.5 plus 2 times negative 285.8 plus 74.6.
Is it a plus? I thought we subtracted it.
So we subtract a negative number.
Subtracted.
It's a negative number in the
sign.
Huh?
I thought we had to flip the sign.
If you subtract a negative number, that's the same as adding it, a positive number. So negative delta HF is positive 74.6.
Yeah, and then I thought we had to subtract it per the.
So this negative sign is that subtraction sign.
Oh.
You're doubling down on that process.
I am.
I'm saying I want to add all these numbers up, and to do so, I need to flip that sign.
Oh, but I'm doubling it because the CH4 in the table is from the product side. So I thought you had to flip that, but then I thought you minus it, so you flip it again. But that's wrong.
Watch, if I would subtract 1 times negative 74.6, then that's the same as adding 74.6.
Yeah, I have another negative in there in my brain, but I guess that's wrong.
Well, I'm sure you're not the only one that's confused. So let me show you. Let me show you mathematically what I mean by that. So This is saying, if I were to just use this without doing all those reactions, I would say 1 mole of carbon dioxide times negative 393.5 plus 2 moles of water times negative 285.8. All right, all of that, let me use my highlighter. All of this is this part of the reaction. Everybody with me? Minus 1 mole of methane times the heat of formation of methane is negative 74.6. Plus 2 moles times 0. So when I subtract that negative number, it's the same as adding the positive number.
Okay, cool. That makes sense. I guess I just got confused where we were. I guess I just misunderstood when it was we were changing the CH4 from a product to a reactant.
Right. So maybe I was trying to reach too far. So I was trying to illustrate that this is an application of Hess's law. So when I get the delta HF from the table of negative 74.6, it relates to carbon plus hydrogen yielding methane. Yeah?
Yeah.
So when I flip it for this reaction, I flip the sign. So I make that a positive 74.6.
So you're just doing that because you know the subtraction sign in the equation.
I'm doing that because by Hess, if I flip the reaction, then the delta H needs to be the opposite sign.
Okay.
And so what I'm doing to these numbers, Emily, is I'm just adding them up. I'm not subtracting anything at this point.
Okay, yeah. No, that's where, yeah, no,
That's probably where I was confusing.
I understand it now completely. That's great. I'm glad we got to go through it again. That's my brain.
I'm sure you're not the only one that's glad. I'm going to let this one be a thought question because I do want to get to calorimetry. But before I leave this topic, and we're going to review this topic when we get back to the lab portion, because again, this calculation comes in the lab. Does anybody have any questions about just functionally how this relationship works? I probably overcomplicated it by trying to show you how it's an application of Hess. You can always just use this mathematical relationship and don't do anything to the signs. Just use this mathematical relationship. So the energies of the products minus the energies of the reactants.
So just to clear that up, sorry, my brain is super fried. But the steps that you just went through, this is you using Hess to kind of break it all down for us. But if we want to try to simplify it, we'll just use that relationship of the delta H naught up top that you highlighted.
That's right. If the problem asks you to calculate a heat of reaction, just use the tables in the back of your book. Don't worry about showing Hess.
Okay.
I just did that to show where the mathematical relationship came from. But probably that's not what you needed from me in week 11. So I'll revisit that for next semester. All right. I want to get to calorimetry because that's really where your lab is today. This is a sample coffee cup calorimeter. What are all the cues that you might see in this setup? Where could energy be gained or lost? I'll tell you right now, you're putting a reaction into that coffee cup. So a reaction is going into that coffee cup. I want to get us to that first law of thermodynamics, which says all the energy in the universe only changes form. We don't create or destroy energy. So what are the cues that could happen in this process? Just list them. What could give heat? What could take heat? I'll give you one for free. The reaction. It could be endothermic, it could be exothermic. We don't know. In the lab this week, you're going to try to figure out a delta H for 3 different reactions. What else?
I think the glass stir.
Okay. The stir, I agree. It's stirring up the reaction. It's right there in the mix. Literally mixing. It could take some heat. I agree.
Thermometer.
The thermometer.
The cup.
The cup.
The lid.
The lid.
Outside environment, if it's loose fitting lid.
You're right. The air around. Remember, this is going to be an aqueous reaction. I wouldn't have told you that if it wasn't meaningful. What does aqueous mean?
In water, so the water or whatever solution is in.
Correct. The water around your reaction is a surrounding. So the solvent is not part of the system. It is a surrounding. Okay. All these things, the stir, the thermometer, the cup, the lid, the air that's above your solution in the cup, all of that relates to the calorimeter. And generally in these calculations, we just put a single Q that relates to all of those. We don't measure the heat capacity of each of those individual items. We measure the overall heat capacity of a calorimeter, and we give that a big C.
Professor, does that also include the air?
Yeah, I just, whoop.
Oh, okay. Thank you.
But I mean, what I mean by that is the air in the cup. Every single calorimetry calculation you do for me in the textbook or on practice problems or in the lab, we're going to exclude the air in the environment. We're just going to assume some heat gets lost to that, but it never goes into the calculation. The air that I'm talking about is maybe the air that's in the headspace above your solution. Gets captured in this calorimeter constant, the heat capacity of your calorimeter times delta T. That's generally the term that we use to apply to the calorimeter contribution, or CAT. We've learned so many Qs so far. This is one more Q that relates to your calorimeter. The reaction itself, if you'll remember from our discussion last week, the Q of a reaction is a Na, N delta H, where N is moles and delta H is the enthalpy of the reaction. What do you think the Q for water is? What type of Q calculation? Why did I do that? Because I like to say that Q is a SMAT. SMAT, where S is the specific heat of water. What is M?
Mass.
Mass. Okay. a huge part of your thermochemistry problem solving is going to be identifying the cues. What cues are involved in the heat transfer process that you're studying? So again, all of these mathematical relationships will be on your potentially useful information, but you have to know what these variables mean and when to utilize which form of cue. I want to focus on our lab today. If I were to draw at the molecular level, the species present in a cup with aqueous HCl, what species would I draw? I'd love for you to annotate my screen. So to do so, you should be able to go up to your view options. Maybe it's there, or maybe it's in the toolbar at the bottom. There should be an annotation. You should have the ability to annotate. Or you can unmute yourself and tell me what to draw. I don't know why I don't have the ability to annotate my own screen. Do any of you have the annotation option right now?
I don't see it.
Yeah, I don't either.
I wonder if that's a security setting. How come we get to do it in? Oh, well, tell me what I would draw. It's not worth figuring out right now.
Hydrogen and chloride ions being separated in water solution.
Perfect. I see ions. I have ions. Okay. Just after, I'm going to add some sodium hydroxide to this solution. So I still have all those ions I had before. What else do I get? I'm going to add sodium hydroxide.
Sodium.
More ions.
I get some sodium ions and what?
Water.
Some hydroxide ions. These are all the reaction ions that are in the mix on my reactant side. Okay, I got all these ions together. What does this reaction produce? I heard somebody say water. I agree. It produces some water. What's the other product?
Salt.
Hmm?
Salt and NaCl.
That's right. I'm still going to have some sodium ions, and I'm still going to have some chloride ions. So overall, what is the NIE for this process? Maybe I'll start with the BME. The balanced molecular equation is hydrochloric acid, sodium hydroxide yielding liquid water, and sodium chloride. My question was, what's your NIE? Your process should be underline anything that's solid, liquid, or gas. Circle anything that's a weak electrolyte. You folks are still weak on weak electrolytes. That's an area where you need to practice. So I gave you a list of strong acids. Any other acid is a weak acid. So review that. Think about that. That's a place where that's a growth area for many of you. Okay, I'm not going to circle anything because hydrochloric acid is a strong acid. My NIE is going to produce some of that water. Well, what ions produce the water? H+ ions NOH minus ions. So there's my NIE. This is your system. This right here. This is the system. Everything else is the surroundings. Those spectator ions are not reacting. This is the system. This is what's changing. But can I get rid of those spectator ions? I cannot. They're always going to be present. So what you're going to see in this lab is that when we do the Q of H2O, we're not going to do the Q of H2O. We're going to do the Q of the solution. So you're going to take a specific heat of the solution, and you're going to take the mass of the solution, including the ions. So you're going to be given a density, and you're going to use that density with the volumes measured to determine that mass. So I just want to emphasize that there are ions in solution. So the density of your solutions is a little more dense than water. Your heat capacity of your solutions is a little less than water. Okay. And in the lab calculations, you're going to be given those values before every calculation. I just want to emphasize that the delta H that you're talking about, and that you're going to try to find, relates to these ions exchanging. This is one of the 3 reactions in your lab. So from this perspective, the system are the ions. I basically gave this away. The system equals H plus and OH minus, yielding that liquid water. That reaction is the system. The spectator ions and the solvent are the surroundings. The lab protocol asks you to consider the calorimeter, but since we're using Beyond Labs, it seems like the Beyond Labs platform has engineered the platform such that you don't need to really account for the calorimeter absorption of heat as much. So we're going to we're going to ignore the calorimeter contribution in this lab. So you might read about that in your lab manual as you're making your pre-lab, but we're not going to account for the calorimeter in our calculations for this lab this semester.
Professor?
Yeah.
So as a rule of thumb, if we ever get a net ionic equation, that's always our system, or was that just in this case?
That's why we emphasize it in this class. The net ionic equation is the only thing that's changing in a chemical process. So yes, the NIE for any reaction is always the system. Just those ions forming the products. But what I really mean to emphasize is that we have to deal with the Q of the solution. We can't ignore that there's solvent around that, and that the solvent is what's absorbing or providing most of the heat that reaction needs, whether it's endo or exothermic. So pulse check, if our reaction is exothermic, what should happen to the temperature of our solution? Up or down?
Down.
Wait, did you say endo or exo? Wait, what did you say?
Exothermic, should my temperature go up or down? If this delta H has a negative sign, should my water get warmer or colder?
Warmer.
Correct. If those ions reacting to produce water release heat, then delta T should be positive. I should get warmer. Let's think about why mathematically. In this lab, we're going to have the reaction that we're interested in, and we're going to have the surroundings, which is the solution that reaction is contained in. And we're going to ignore the calorimeter. I want this to be a thought question. We are ignoring the calorimeter. Should that make the delta H that we calculate be too low or too high? I'm going to leave this in the parking lot for you to go do your lab and actually immerse yourself in these calculations. I don't think you're ready to answer this right now. So this is in the parking lot for when you're ready to come back out to the car. Okay, so I just parked it out there. When you go through your lab and you're asked to do some error analysis at the end of the lab, this is a key question for you. We're ignoring this. What would that assumption likely do to your delta H? We're only going to confront these two in the lab. So for a reaction, remember, we're going to use Na. And for the solution, we're going to treat it like an object. So we're going to use a SMAT. The thing that we want to know is delta H. So I want you to rearrange and solve for delta H. How would I rearrange those variables and solve for delta H? So I'm gonna delete SMAT from both sides, or sorry, subtract SMAT from both sides. So I get negative SMAT equals N delta H, and I'm gonna divide both sides by N. So delta H naught is negative SMAT over N. You have 3 different reactions in this lab. So N is going to be moles of sodium hydroxide in trial 1, or moles of water that you produce in trials 2 and 3. So when you're calculating N, that's moles, and moles are going to be the sodium hydroxide that you use in reaction 1, or the product of water in reaction 2 and 3. I want us to do some sample calorimetry calculations that mimic the lab. So this one's pretty similar to what your lab is going to be. I want you to just read through the problem before we work it together. So read through, think about, this is a standard question about calorimetry. So what data is there? What assumptions does this problem make? The only thing I'm going to change about how I worded it is I want you to think about this from the amount of water produced. Okay, I read through this and I read that we have 2 things reacting. This is a chemical reaction. I'm reacting sodium hydroxide with hydrochloric acid. Both of these are aqueous. So I'm going to make salt water as my product. Okay. I'm told some things. I'm told that I'm going to mix 25 mils of a 1.010 molar solution with 25 mils of a 1.004 molar solution. Each of these are at 25 degrees Celsius. After the reaction, my thermometer reads 31.9 degrees Celsius. What should be the sign of delta H?
Negative.
You got it. How did you know, whoever said that?
If temperature is increasing, means delta H is negative. Like if we feel heat, it's exothermic.
So 31 degrees is higher than 25 degrees. That reaction released some heat. If you release heat, then delta H should be negative. Okay, what is the change in enthalpy? That means this question wants to know delta H. What is the change in enthalpy for this neutralization reaction? Assume a specific heat capacity of the reaction is the same as that of water, and that the density of the solution is 1 gram per mil. Okay, did this problem ask anything about a calorimeter? Or tell you anything about the calorimeter? It did not. So this problem, much like the lab, is going to ignore the contributions from the calorimeter. We're not going to put that in our Q's. The only two things it's telling us about are the reaction, and it tells us assume that the reaction mixture, so it's telling us about the mixture and some properties of water. So we're again going to account for that solution, just like I've been leading you up to. This problem is built to mimic what your lab looks like. So just like we did on the previous page, we want to know delta H, which we just solved to be negative SMAT over N. Everybody with me? So which of these variables, I need to build the relationship that's going to help me solve this. So S, what is S in this relationship? I'm going to highlight it with orange. What does S stand for?
Solution.
What about the solution? It also starts with an S.
Specific heat of the solution.
Specific heat capacity. So here's my orange number. I know the heat capacity of the solution. Okay, what is M? And put it in green. What does M stand for?
Mass.
Mass. How am I going to find the mass of the solution?
Density.
I'm going to use density and
Volume.
volume. Density times volume is going to be mass. What volume?
Volume of HCl and NaOH.
You said both. Am I just going to use 25?
Both of them added.
Yeah, I need the total volume. Okay, so I'm going to take that density of water and I'm going to add the total volume. So I'm going to get 50 grams. Okay, here's my mass contribution. I'm dealing with density and the total volume. Okay, delta T. What is that? What does delta T stand for?
Change in temperature.
Change in temperature. So I know an initial, I know a final. So delta T is the final minus the initial. Okay. What is N?
11.9. Oh, sorry.
What's N?
Moles.
Moles of water produced. How am I going to find that?
Take molarity of the solutions.
I'm going to need some molarity. What else am I going to need?
Volume.
Volumes of solutions. What type of problem is this? Starts with an L.
Limiting.
A limiting reactant. It's a limiting reactant problem. I have two amounts of two different reactants. So one of these is going to limit how much product I can form. Which one? If you're not sure, what should you do?
Work out the theoretical yield and see which one's the smallest.
How do I do that? I dig two what?
Mole tunnels.
I dig two tunnels. But since all of these are 1 to 1 to 1 and these are equal volumes, which one do I know is going to limit me?
The 0.004.
That's right. The lower molarity. That's going to be my limiting reactant. Since these are equal volumes, everything is 1 to 1 to 1 to 1. The fewer moles per liter is going to be my limiting reactant. So I can dig my tunnel starting with that 25 mils of sodium hydroxide. I'm going to get out of mils and into liters so that I can get out of liters and into moles. But I want to know about the amount of product that I produce. So I'm going to take this into moles of water. So 1 to 1, 1.004 moles per liter, and I get 0.02510 moles of water. So I can plug in for delta H. I can solve for delta H. I'm going to put in my specific heat, 4.18. So I'm sorry, it's negative SMAT. So negative 4.18 joules per gram degree Celsius times my mass, which is 50 grams. So grams are going to go away. Times delta T, which is 31.9 minus 25.0, which is 6.9 degrees Celsius. So degrees Celsius is going to go away. Times 1 over my moles, which are 0.02510 moles. But the problem asks me kilojoules per mole, and right now I'm in right now I'm in joules. So the last thing I want to do in my tunnel is get out of joules and into kilojoules. There's 10 to the 3 joules per kilojoule. So I plug and I chug. What do I get?
I got negative 57.454.
Yeah, same.
Okay, negative 57.454. How many sig figs can I keep?
3.
Nope.
Oops.
Here's the tricky part about thermochemistry. When you start subtracting temperatures, you're going to be eliminating sig figs. So that change in temp only has 2 sig figs because you're only significant to the place value of least significance. So you only have 2 sig figs in that final answer. So negative 57 kilojoules.
Is it only 2 6 figs because we don't count the 0 and 25, or is it because the difference is 6.9?
It's because it's an addition and subtraction, which means we are only significant to the place value of least significance. So I'm only significant to the 10th place. That delta T only has 2 sig figs. The rule for addition and subtraction is different than the rule for multiplication and division. That's right. This is my final temp minus my initial temp. Oh man, I'm running out of time. How are we doing?
Slightly less confused.
This is very similar to, excuse me, this is very similar to what your lab calculation will be. So I initially had thought we would have time to go into breakout rooms and do all this, but ain't nobody got time for that. I'm beginning to realize. So let's talk about this together. these are the 3 reactions you're going to be doing in the lab. And this lab is called Hess's Law. The lab is called Hess's Law. In these reactions, you're going to be measuring a delta H naught. Why is this a delta H naught and not simply a delta H? What does that degree symbol mean? If you're not sure, go back to page 6 of your lecture notes. What does that delta H degree symbol mean?
Standard conditions.
Standard conditions, which are what, Chris?
1 atmosphere. 298 Kelvin.
And these are aqueous reactions, so what else?
1 mole.
1 molar. These are going to be 1 molar solutions at 1 atmosphere and 298 Kelvin. How can I use these 3 possible steps? You're going to have to pick out which one you want to be the net reaction. How can I apply Hess's law with these 3 reactions? What are your thoughts? I want to build a mathematical relationship that relates delta H1, delta H2, and delta H3. I'm going to let you all talk this out amongst yourselves as a group. I'll tell you right now, let's don't make reaction 1 be the net. Pick reaction 2 or 3, whichever one you want.
How does people feel about 3?
Okay, Gerardo has weighed in. He says this is going to be our net. That's the one we want to know. So how can we use our steps to build that net? Find a species in reaction 3 that's only present in 1 possible reaction step.
HCl?
Great, perfect, Tajay, HCl.
Oh shit, I was right.
Of course, she's a chemist.
Nice.
Okay, do I need to do anything to reaction 2? Do I need to flip it? Do I need to scale it? Or is that species present in the place it needs to be present?
It's present in the space that it needs to be present.
That's right, so I don't have to do anything.
Okay, I'm on a roll.
All right, how do I manipulate reaction 1? Or do I need to? If I just add reaction 1 to reaction 2, do I get reaction 3?
Okay.
We're going to use reaction 2 as is. What do
Like
I
you-
need to do with reaction 1?
Like
Does it
when-
need to stay the same, or does it need to flip, or do I need to scale it? What needs to happen?
Do you need to flip it for the product to match up with the NIE?
So if I flip it, I'm going to put aqueous on this side and solid on that side. Is that what I'm hearing, Alex?
I'm guessing.
Okay. So what happens when I do that? That solid is going to go away. I'm going to have aqueous sodium hydroxide. And then I have sodium chloride and water from reaction 2. Does everybody see that?
Yes.
So if I swapped reaction 1, what did I do to delta H of reaction 1?
Inverted it.
Mathematically, what do I do to it?
Negative.
Negative.
negative delta H1. Everybody see that?
Yes.
Okay. Well, since I'm a positive person and I don't like negatives in my life, you're going to see most of my pre-lab videos are going to refer to delta H2 being equal to delta H1 plus delta H3. But mathematically, these are equivalent. All I did was add H1 to both sides. Okay, so you're going to see me refer to this mathematical relationship in the video and talking about the calculations, but mathematically, those are equivalent relationships. Does everybody see how this is an application of Hess's law? I'm taking these two-step process equal to a one-step process. I'm trying to see if the delta H's that I calculate for a two-step process are equal to the single step. That would be a validation of Hess's law. Everybody see where I'm going so far? Okay, how am I doing on time? I got 12 minutes. Let me show you how to do this next part of the calculation. We might not get through all three of these, but let's see if we can try. Linking out to that enthalpies of formation, how can I calculate delta H naught from enthalpies of formation? So let's just do reaction 1 together. Reaction 1 is sodium hydroxide. I want to, for the purposes of what I'm about to do, I want to use the reactions as they are. Let's just focus on the reactions as they are. Because that, oh, sorry, undo. That more mimics what's in your, I don't want to flip any signs. I want to use this particular relationship. So adding 1 and 3 to make 2. I think this is confusing enough as it is. I'm going to put up the formula from page 6 and 7, which says delta H naught is equal to the sum of the moles of the products times the delta HF of the products minus the sum of the moles of the reactants times the delta HF of the reactants. So in reaction 1, my product is sodium hydroxide aqueous. Somebody who was able to access those tables, can you give me the number, or is it in my, it would be awesome if it was in the one I put in your lecture worksheet. Nope, not awesome. So it's not, when you look at those tables and tables of data, if you have a compound like sodium hydroxide, you're going to look at the sodium portion. So it should be, sodium hydroxide should be in the sodium part of your data tables.
I have my book open if you want any numbers.
Yeah, I'm asking. So I want the product number. I want sodium hydroxide aqueous.
Aqueous is negative 470.1.
And how many moles of sodium hydroxide aqueous are in my reaction? 1. The molar coefficient is 1. So when we look at this NP, this is the mole coefficient in the reaction itself. It just so happens for every single one of these reactions, every coefficient is 1. In problems in your homework set, that won't be true. So this moles relates to the mole coefficients in your reaction, just to be super clear. Okay. So, but Emily was right. I've got negative 470.1 kilojoules per mole. And I'm going to subtract 1 mole times the sodium hydroxide solid. So Emily, what's that sodium hydroxide solid?
Solid is negative 425.8.
All right, I'm going to do that math. I'm going to add those up. What do you get? Just so you know, you're doing your lab right now. So these are all required for your lab. So I'm not going to give you these. You got to do it. You got to earn it.
I have it, but I've been talking a lot, so I don't know. If
I agree.
Yeah.
Negative 44.3.
Me too. Okay, that's delta H1 for reaction 1. I want you all to take the wheel and tell me what to write for reaction 2. Reaction 2. Applying this relationship. Sum of the moles of the products times delta HF of the products minus sum of the moles of the reactants times delta HF of the reactants. What's a product of reaction 2?
CL aqueous.
NaCl aqueous. So, Emily, what's that one?
Negative 407.2.
All right. Are there any other products?
Water.
Water. What form of water?
Liquid.
Liquid. States of matter, matter. This one is earlier in your worksheet, so I remember that one. All right. So here's my sum of the products. What's a reactant? I've got sodium hydroxide solid and hydrochloric acid aqueous. Okay. So I'm going to subtract. I'm going to put it down here because I'm running out of room. 1 mole times sodium hydroxide solid from my earlier reaction was negative 470.1 plus 1 mole times hydrochloric acid aqueous.
Mine's separated, I think, in my version of my book. So I have hydrogen plus is 0. Oh, and chloride is probably something that is somewhere. Cl minus is negative 167.1.
So if you're having a hard time finding it, that would be in the chlorine section, since chloride is the unique ion. For those of you who are not looking at your book right now, the tables and tables of data are disaggregated by atom, special atom in the formula.
It is alphabetized, and I think that is my problem. I do not know the alphabet at this point in the day.
All right, do the math. What do we got? Oh, wait, I took the wrong value. It's not 470 is the aqueous. 425.8 is the solid. Sorry. I can't keep myself straight at this point in the day. Don't all jump at once.
I can say it, but I didn't want to talk because I
Negative
talked
50.
too much. Oh, go for it.
Negative 55.8.
Is that for? I'm confused. Maybe I wrote my numbers down wrong.
Minus 100.
That's what I got. But I think you got the other number from the wrong answer that I put before, which was the 470.1. So the answer that whoever called that out,
That was me. I changed, yeah.
yeah,
have-
I think you
Still
used,
have the old number.
I think you used my old number. So that's probably my bad. Not probably, that was definitely my bad. Okay, so delta H3. This will be reaction 3. So let's go through this very same process. You figure out what are your products. What are the delta HFs? It just so happens that reaction 3 and reaction 2 have the same product. So that's going to be the same math. Negative 407.2 plus negative 285.8. But we have different reactants for reaction 3. So sodium hydroxide aqueous and hydrochloric acid aqueous. So we're going to subtract this time negative 470.1 plus negative 167.2. So Kate, what'd you get? Negative 55 point.
Negative 55.8.
I think I got 7. Did I do something wrong? These should add up to a whole number. Minus 0.3 should be 0.7. I think I'm right because
Oh, you're right, because I did put in 167.1 accidentally, just like a typo.
okay. Apply this to Hess's law. Did the relationship that we came up with above work? I'll remind you what we came up with since I might have erased it. No, I didn't erase it. Is this true? Is delta H2 naught equal to delta H1 naught plus delta H3 naught? So delta H2 is negative 100 kilojoules. Delta H1 is negative 44.3 kilojoules. And delta H3 is negative 55.7 kilojoules. Is Hess's law a law or a theory? I'm going to say from this data, confirmed. Okay, ideally, when you're measuring in the lab, the experiment, it should be a confirmation of Hess's law. I am out of time, folks. And there are definitely more problems in this problem set. And it feels like you might be a little bit overwhelmed with what's going on. So I want you to focus on applying what we just talked about with respect to the lab and maybe actually trying to collect some data for the lab, review those Hess's law calculation videos. And I'm going to put a bomb calorimetry video up on the recap page. That's the last topic in this worksheet that I wanted to talk about. Don't make that your highest priority. We just talked about Hess's law and calorimetry, and that's really applied in the lab. So make the lab your first priority. Come back to bomb calorimetry at the end. Thank you for your attention today. Please let me know if you have any questions. I do have office hours tomorrow from 3 to 4, every Monday and Tuesday night from 8:30 to 9:30 at night. I apologize. I'm not totally done caught up on grading, but I'm working my hardest and I'll get there soon, I hope. I keep saying that, but I really do hope I get caught up soon. Thank you for all your hard work.
Copy
Thank
paste
you,
back at
Professor.
I have a question regarding your law and theory joke.
Mm-hmm.
Isn't technically it better to call it a law because it has that standard enthalpy conditions?
It's a law because it's math. Anytime
Okay.
you call things laws in chemistry, it really relates to a mathematical function.
Okay, so if there's math involved, it's probably a law. And if it's just words, it's probably theory.
Correct.
Okay.
That's generally true. I'm not going to say that's true for everything, but generally, I think when we say things are laws, there's like a mathematical relationship. So the first law of thermodynamics, 0 equals Q1 plus Q2 or E1 plus E2. That's math. All right, friends. I'm gonna go eat lunch. It's only like 2:30.
Hey, Professor, can I make one quick recommendation?
Uh-huh.
And I'll definitely fill out the survey in depth and give you like any feedback. I mean, like off the bat, you're doing everything right. Like we're screwing up. But if I can offer one anecdote, I've been like keeping statistical analysis of like how many students we have at the beginning and how many start dropping by the end of the class. And we usually lose anywhere from 10 to 20% of the total class roster, I guess. So I was just gonna ask, would you be interested in offering us like a 5 or 7 minute break, like in between? Do you think maybe that would help in keeping people here?
I only get you 2.5 hours a week.
I know, but I just was trying to figure out a way to keep people in here. So
You
that
think,
was
you think me giving you a break in the middle is going to encourage people to stay tuned?
no. I guess when you say it out loud like that, that doesn't sound
I think
right.
quite the opposite, but I do hear you, and it is a lot. There is a lot that goes on. So I totally hear that feedback, and I agree that I need to build in a break. I just don't know how to.
No, I
Like,
know, because I totally agree with you. It's just only 2 hours. I'd rather like I sit here, I wait to pee until the end. So
and it also, the other thing that's also true is I feel like I waste a half an hour like going through what the module looks like at the beginning, but at the same time, I feel like it's important to communicate what's on the board for the week. So like I don't want to give that up either. But
for sure. Well, then for what it's worth, I think we're all just making do with what we can. So please don't feel like you need your methods aren't like good.
well, for what it's worth, we've only got 2 more lecture periods with me.
Oh God. Yeah, we have,
Everything else is assessment. So
yeah,
I'll try to build a break into those 2. How about that? It's a deal.
sounds good.
I think the reason that you see people chiming out or tuning out is because I didn't put points with the lecture anymore. But, and because I post the recordings.
Oh, there are points. They're just all in the assessment.
Oh, that's correct. I'm glad you recognize that.
Oh no, no, I've done this pony show enough times. I'm not no, no. Okay, well you're starving and we should be doing our homework, so we'll let you get on with your life and we'll get on with ours.
I'm glad you came, and I didn't mean to be cavalier. I welcome the feedback, and I know
No,
that
I know. It's just like I'm as desperate as you. It's like for the love of like what do we need to do? Like pay do we need to send people money? Like I don't know.
send people money for what?
I don't know, like literally paying them to stay in class. I don't know. Like it's just like a desperate mind, just like looking for any logical way to get people to. It's like
Hey,
this is literally your grade.
I'm
Everything you need to know is the exam. I
I'm
went through your study notes with it, like the problems that you prepped us for helped us in the assessments. Like you guys are ungrateful bastards.
you didn't hear any of that from me. You're paying me. Like I'm doing this as a service, right? Like you have
Oh yeah, no. Well, thank you for
you
your
paid a
service, man.
tuition for the units, and so I'm giving you what you paid for. So I mean I don't comment. Everybody's got life going on. I'm
You
not.
know, but you work
That,
so hard, and we notice, so we appreciate you.
it's fine. I'm here for you. So anyhow, my promise to you is you don't have to look at the bomb calorimetry video tomorrow. Just focus on the lab and get the lab. Look at the bomb calorimetry in a little bit.
Cool. I plan on showing up in office hours just to do my lab and ask any questions.
All right, please do, because that lab is a monster.
Sweet.
Thank you. Enjoy
Thank
your
you.
lunch.
Peace out, everybody.
Bye.